Hi everyone, a warm welcome to my talk today. This is a recording of my talk at Models of Consciousness 5. And before I start, I'd like to thank all of the other organizers of the conference, and in particular the participants, for a wonderful time. I had a great week. I enjoyed the talks and I enjoyed the discussion sessions very much. So thank you all for coming to Bamberg. Okay, this is my talk, and my talk is devoted to three notions: computational phenomenology, mathematical phenomenology, and pre-reflexive self-awareness. And I'll introduce these notions, of course, and I'll start by introducing mathematical phenomenology and computational phenomenology. And I thought that's very good, just to see if we have clarity on what we all think we're doing when we're engaging in these things. So mathematical phenomenology, on my view, can be characterized as the use of mathematical tools to describe or represent phenomenology. Mathematical tools, most notably, are mathematical structure or mathematical formalism more generally, and we want to describe or represent phenomenology. So what we have on the one hand is mathematics, and I want to emphasize that for the purpose of that talk, and on my view also more generally, mathematics is really just another language, a very different language, but a language that we can use. For example, in this context, to describe or to represent phenomenology, just as any other language. I crossed out the word realm here because I don't want you to think that mathematics is like a part of reality for the purpose of that talk, necessarily at least. Okay, so that's mathematical phenomenology, very simple. We use a language, it happens to be math, to describe phenomenology. What is computational phenomenology? Well, computational phenomenology roughly is the application of formal tools from computational modeling to account for phenomenology. So here's phenomenology again. And here are the computational tools. So in the most recent version, if you like, or in the most recent age of computational phenomenology, the tools that are being applied are from the free energy or active inference framework from Carl Friston, and co-authors, I should emphasize. So we have these computational tools, and we want to use them to account for phenomenology. And account here really means more something like explaining or modeling. So that's something very different from the mathematical phenomenology, which we've just seen. So in a sense, what we're doing here is we're doing something which is more similar to building theories or models of consciousness. They are not necessarily full theories. They might not necessarily target the distinction between being conscious and not conscious. But what they do is they want to somehow explain, model, or more generally account for some aspect or part or feature of phenomenology. So in saying that they are similar to theories or models of consciousness, I'm presupposing a specific understanding, which in my view is the most general understanding one can have of theories and models of consciousness. But of course, there could be different ways of using these terms. So when I say theory or model of consciousness, what I mean is a hypothesis about how phenomenology and the subject matter of the sciences relate. So usually, or in many theories, and specifically in the context of the most recent version of computational phenomenology, we're interested in the brain on the one hand, and where the theory would express a hypothesis about how any description of the brain on various different levels could relate to conscious experience. And just to emphasize, so by phenomenology, I really mean sort of, if you like, lived experience. It comprises terms like phenomenal character or qualitative character, as indicated here. Okay. So these things are different. On the one hand, we have computational phenomenology, summarized again here, the characterization, and mathematical phenomenology. So how do these relate? Well, if you want to make two premises, then we can say something about the relation. So the first premise would be that formal tools from computational modeling are mathematical tools. I consider this obvious. The second premise is that an account or explanation of phenomenology requires a description or a representation of phenomenology. I think that's true in particular, but strictly speaking would suffice if that were true of accounts or explanations of phenomenology in terms of mathematical tools. And then if these premises are true, it follows that computational phenomenology requires mathematical phenomenology. So the fundamental idea being that if you want to describe or build an account, if you want to build an account as illustrated here, you first have to think, or it requires you to think about how mathematics can be used to describe or represent phenomenology. This is the fundamental idea. And I put this as an argument just because philosophers like arguments. But I should say I really believe that this is the case. I think that if we want to do computational phenomenology, we have to think about mathematical phenomenology. Computational phenomenology is doing mathematical phenomenology and then something in addition. And I'm saying this because this relates to my work. So one core theme of my work is work on the foundations of mathematical phenomenology. And I should say this just in case you look at the literature. So I take mathematical phenomenology just as quality spaces or phenomenal spaces and a few other things to be instances of mathematical structures of conscious experience. So I'm using that term here really as a complete term to denote to have an umbrella term for all of these instances where we use math and want to attribute it to conscious experience. So one fundamental question I'm asking in my research is, what are the truth conditions for ascribing mathematical structure to phenomenology? Yeah. This is essentially the question, how do we do mathematical phenomenology? And also, how do we build quality spaces? Yeah. And just to make it very clear what I mean by that question, with the truth conditions, here are sort of other ways of putting the question. I want to ask, what does it mean to say that conscious experience has a certain mathematical structure? Yeah. What is the meaning in saying that? Or another way of putting it is we can ask, what defines why conscious experience has one rather than another structure? Yeah. Which definition are we presupposing when we attribute one rather than another structure? And I think that only once this is clear, it's a very fundamental question, can we actually talk about what is the right or what is the actual structure of conscious experience. So that is sort of a core theme in my research. And I now want to explain a few things about that core theme and how that relates to mathematical phenomenology, and in virtue of that, to computational phenomenology. And in moving forward, I'll be using a term, namely the term methodology, and I'll be using it as denoting a collection of methods, practices, procedures, and rules used by those who work in some field. This is not what methodology can also mean in philosophy, but I'm presupposing this meaning now. And in the present context, the meaning is the collection of methods, practices, procedures, and rules used by us in consciousness science to ascribe mathematical structure to phenomenology. So what is the relation between methodology and phenomenal structure, if you like, or mathematical phenomenology? Well, I think we all agree that if we use technical terms like qualities or qualia or consciousness, we have to have, in the best case, definition, but at the very least, we have to have conventions about what these terms mean. If we don't have definitions or at least conventions, we can't really engage in studying these properties or these terms, these concepts. Well, the same holds true also for mathematical terms, even so we're somehow less open to the fact when just behaving naturally. So if you use a mathematical term, specifically if you attribute it to consciousness, you have to understand what it means. The difference between the two cases, like concepts and mathematical concepts, is that in the latter term, in the case of structural mathematical concepts, these definitions or conventions are often already methodologies in the sense just presupposed. You can think about quality space. If you say what a quality space is, you're already saying something about what happens in a lab according to most understandings. And the point I want to really drive home, and that's something I really care about, is that it does not make sense to talk about phenomenal structure or mathematical phenomenology or structure of conscious experience independently of such definitions or conventions. It just doesn't make sense. To the exact same degree that it doesn't make sense to talk about qualities without having at least a convention about what we mean by that term. And this is important because we can use different approaches to describe one and the same experience, or if you like here, one and the same phenomenal character. And depending on which methodology you use, you get a different mathematical structure that represents or describes this experience. And we have to keep that in mind. So we can't fight about what the right structure is without saying what we mean by ascriptions of structure to mathematics. Okay, this was sort of a warning slide or something I just want to say because I think it's important. But let's go back to the fundamental question. Let's look at an example. And the example I want to look at is awareness of awareness. And specifically, I want to look at awareness of awareness in MPE no absorption episodes. That's because the MPE track, the Minimal Phenomenal Experience project, was a large part of the conference, and I think there were a lot of interesting interactions. So I just wanted to take that as an example and then also develop it a little bit further later in the talk. So awareness of awareness is what people sometimes call pre-reflexive self-awareness. There are a few other terms also, but it's the idea that you're aware of being aware. Now, if you look at the MPE website or at this paper, you see that there are already models out there for awareness of awareness. And these are computational phenomenology models. So they don't only seek to describe it in terms of some formalism, but they seek to account for it in terms of some computational method or tool that comes from, in this case, neuroscience. And I won't explain the model here in more detail for time purposes. I'll probably run over time anyway. Sorry about that. But you can check out Lars's talk, which should be in the same playlist that you're watching this talk, and he'll explain that in great detail. The most important part is that you have this hierarchical layer of free energy processes or active inference processes. And you see that the upper layer here relate to the lower layer, and they influence something that's called precision. But I'll just leave it at that. The example I want to throw out is if we look at this structure here, and specifically this hierarchy, we can ask, not is that a right or wrong model, but we can ask, why does this model represent the phenomenology of awareness? So what's the understanding of attributions of mathematics to phenomenology so that this model is being, or that motivates this model as being proposed? Here you see again these precision arrows that control the various levels. But please check out Lars's talk, which is wonderful if you want to have more details. Okay, so that's an example of where the question pops up. And what I'll do in the following now, I'll present you with a proposal for the truth conditions of ascriptions of mathematical structure to phenomenology that is based on existing quality space methodologies. So it's not invented out of thin air. It repairs problems of these methodologies. And there are conceptual problems and there are practical problems. And I won't go into the details in this talk. So you can check out other talks or maybe a paper if you like. But these problems are so extreme that you cannot use these existing models, at least if you're interested in theory building or model building in the sense applied here. And the proposal that I'm going to present takes as input a choice of subject matter. And what do I mean by that? Well, I mean, the proposal can be applied to, it's sort of the proposal itself is independent of whether you want to apply it to qualities or qualia, or maybe instantiated phenomenal properties, or maybe mereological parts, or some dynamic phenomenal structure, or lived experience. So it's your choice to which of these subject matters in the context of consciousness science you want to apply the proposal. And what I'll do in the remainder of the talk, and that's also something we do in the paper, which I'll just share in a second, is that I'll just use the word aspect as a placeholder term for any of these. So whenever you see aspects, you can replace this word by qualities or by qualia, if you like. It's really just a placeholder term. It's not supposed to have meaning itself. You can also replace it by some meaning of the word aspects. I don't think that's a bad idea. But I'll use it as a placeholder term. Okay. And I should say the work that I'm going to present now is work together with Tim Ludwig. And I'll just like to thank him, one wonderful friend and colleague and co-author. Thank you, Tim, if you ever watch this talk. Okay. So this is, if you like, a foundation of mathematical phenomenology. And I'll come to that quote here from our paper, which you can see up here in just a second. But I just want to give you the intuition first. And I should say this is the first time I'm explaining this. I will then talk about something else real quick and then explain it again, just because I think it's really difficult to understand. Not because it's difficult, but because it's unusual. It's difficult to understand because we don't usually encounter these sort of things. Okay, so we'll start again in the same situation we had earlier. So on the one hand, we have mathematical language. I want to drink a sip of coffee real quick. Thanks for the patience. So on the one hand, we have mathematical language. And on the other hand, we have phenomenology. And now the proposal in its current form makes use of something that I call baseline correspondence. And the baseline correspondence between the mathematical language and the phenomenology is that we can pick a set of aspects, for example, a set of qualities or parts or properties or whatever you like, and a set is already a mathematical term. I'll denote the set by curly A. So if you say, well, what are the qualities in this specific experience? Well, that's a set, and that's already a mathematical term. And that's a baseline correspondence, if you like, between math on the one hand, the abstract language of math, and the concretum of phenomenology. And that's what we'll make use of just in a second. Okay, so what we'll do now is we'll pick a mathematical structure. This black dot here is supposed to be a mathematical structure, and this yellow dot here is an aspect of phenomenology. Could be relative similarity, could be something more complicated. And the point now is that if we can consider variations. We can consider specifically variations in the sense of the variations of phenomenology. So these are changes of one conscious experience into another. It's what you'll do all the time if you imagine something, or what you'll do all the time if you're in a psychophysics laboratory. So we have a change of one experience into another. So for example, maybe I'll see blue and then I'll see red. And because of this baseline correspondence, a change of conscious experience is also a change of the set of aspects. It's, for example, if aspects are phenomenal properties, it is a change in the phenomenal properties that are instantiated, or it's a change in the qualities of one experience as we go from one to the other. And these variations, so if we denote by A the set of all aspects, because of this baseline correspondence, we can represent any change of experience into another experience by a partial mapping, which just takes some aspects, namely those that were in the first experience, and provides some other aspects, namely those which are in the second experience. So that's something we can do because of this baseline correspondence. That's really enough now already to say what it means that a mathematical structure is a mathematical structure of conscious experience. Namely, what we can do is we can now utilize properties of variations in both domains. So first of all, on the mathematical side, variations can either preserve a structure or they can't. So those things are often called homomorphisms or automorphisms. You might know the automorphism group. So the idea is a variation that is a mapping that goes from the domain of a structure to the domain of the same structure, that can either preserve all the structure that is, the relations and functions, or it can not preserve it. And if it preserves it, we'll call it an automorphism usually. So that's on the left-hand side. Well, on the right-hand side, we can also talk about preservation. Namely, we can ask whether a variation preserves the aspects that we have picked up. So it could be, for example, if I experience a relative similarity between two colors relative to a third, it could be that I make a change so that the relative similarity disappears or reverses. That would be an example where the variation does not preserve the aspect. Whereas, for example, if I'm seeing, let's say, orange and red, and then there's a change and I see rose and red, well, that would be a variation that preserves the aspects. And the point is that on both sides, in the abstract domain of mathematical language, in the concrete domain of phenomenology, on both sides, we have this notion of variation. And now we can define the mathematical structure, a mathematical structure to be a mathematical structure of conscious experience if and only if these things agree. That means so the black dot here, which represents a mathematical structure, is a mathematical structure of conscious experience if for every variation that preserves an aspect, the corresponding variation on the mathematical side also preserves that structure. It's as simple as that. And that's summarized up here in the yellow part. So that's sort of a little bit, there are a few details, but not many, which we'd have to consider. That's why I put an approximate symbol here. But we'll say a mathematical structure is a mathematical structure of conscious experience if and only if something in phenomenology behaves exactly as the mathematical structure does under variation. The something in phenomenology is an aspect. We often call this a structural aspect of phenomenology. A structure is not meant in a mathematical sense. You could also call it a higher order aspect. So the idea is if there needs to be something in phenomenology that behaves exactly as the mathematical structure does under variation. And behaves exactly as means that if it preserves the structure, it should preserve the aspect. If it doesn't preserve the structure, it should not preserve the aspects. That's the idea. Okay, so we can symbolize this like this. Yeah, so that's the thing you can keep in mind. The idea would be that we have variations on both sides, and the requirement for something to be a structure of conscious experience is literally just that these variations agree. Okay, so this was very quick, and I'm sure that it was too quick to really understand it. So I'll explain it again in slightly different language in just a minute. But before I do so, I want to say a few other things. So first of all, most importantly, the question is, what are variations actually? So a variation is just a change of one conscious experience to another. What do we mean by that, or what are examples of that? And what I really like about this proposed methodology is that there are two examples you can give, two types of examples. The one are just eidetic variations, right? If you imagine something, you go from one experience to another, both in the imagination and also when going from the actual experience to the imagination. So that's an example of an eidetic variation, as in the work of Edmund Husserl, and eidetic variations are indeed examples of variations. Another example are just variations of stimuli. If I'm in a psychophysics lab and someone is presenting stimuli to me, and they change one stimulus to another, well, that's a change of conscious experience. That's being induced externally, so to speak. And that's another example of a variation. So what I like about this is that this really provides a unification, at least sort of conceptual so far, hopefully in practice at some point. It provides a unification of psychophysical and phenomenological approaches that both use mathematical structure. And I really hope that sort of something along these lines, maybe an improvement of that methodology, which some of you develop, hopefully, could really get us into a position where we can combine the benefits of both realms. Okay, good. So why should we care about this? Why do we need this? Well, I think the situation we're in at present is as follows. So we'll have phenomenology. Is this wonderful image? Was it by Mach? I have the quote on some other page, maybe the next one. Sorry, the source, not the quote. So we have phenomenology, and what we're currently doing is, for example, in the MPE project, which I really love. I think it's an absolutely stellar research project, and I think that will make some deep impact in consciousness science. So we'll study experience, for example, using meditation. And what we do then is that we basically do phenomenology. We use technical terms built on common language to express something about phenomenology with a small p. This is sort of more indicating the movement here in this slide. And then what we'll do is, we'll translate that which we sort of uncovered from phenomenology using common technical terms built on common language. We'll then translate that into mathematics. So here are just a few sources, but there are many more. I noticed that Camilo is missing, so Camilo is working this two wonderful work. And so we're doing this. And obviously, so when we do this, we're somehow limited by our technical common language constructs. It's very hard to go beyond them, maybe impossible, right? And so the hope behind my work on a foundation for mathematical phenomenology is really that we could go from here to here just in one step. We can directly go from phenomenological data to mathematics without having to paraphrase this data first in technical terms built on common language. And what I think about this all the time when I look at this slide is really something like terms like the phenomenology of knowing. I think I get what's being meant by that term. And I get why people use it, because when they learn something, maybe get to know something anew, they basically have a phenomenological experience that they also have in the particular states of deep meditation that this concept may refer to in another context, right? So I get what we do, but the problem is the general language term phenomenology of knowing is very general, and there are just 100 different ways in which we can flesh this out in terms of mathematics, and therefore also 100 different ways in which we can flesh this out in terms of the active inference or free energy principle. So that's my motivation. Examples like this are my motivation for why I just struggle with this way here. I think this is too lossy, if you like, too much information loss going over common language. So the picture I have in mind really is that we have two complementary and mutually inspiring approaches. One approach where we go from phenomenology and we describe it in terms of common language and technical terms, and another approach where we use phenomenology and specifically phenomenological data about variations. And then we use these data and do mathematical phenomenology, and we use technical terms built on mathematical language. And basically, these approaches describe the same type or class or whatever, or subject matter of phenomenology, and could inspire each other and then hopefully get us much better model and much richer understanding. So that's the approach, or the image I have in mind. And I should say, just to be very clear, the idea is not that this here is just limited to some boring part of phenomenology, but the idea is really that mathematical phenomenology can be applied to describe lived subjective experience, just as normal phenomenology. And that could be very helpful specifically in cases where technical terms built on common language do not suffice, as is arguably the case for awareness of awareness or pre-reflexive self-consciousness. Okay, back to the methodology. So I now explain the methodology again with the purpose of then applying it to pre-reflexive self-consciousness in just a minute. Okay, so that's a different explanation of the same idea we just saw. Okay, so let's use a yellow dot again to represent an experience. So this could be any type of experience you can think of, something very simple, something very complicated. And we'll use a blue dot to represent the aspects of that experience here. So same location relative to what's going to come means sort of same reference. So these are the aspects in this experience. And we'll add a few experiences and we'll add the corresponding aspects here. So this is an experience. Those are the aspects of that experience. For example, if you choose aspects to denote qualities, those would be the qualities. If you chose aspects to denote parts, that would be the parts in that experience. Okay. And what the methodology now does is that it considers variations that go, first of all, from one experience to another. And second, so what I'm drawing in here now are variations that only those variations that preserve a specific aspect, and that's a structural aspect, as I already indicated. So something you could call not a first order aspect, but a higher order aspect, like relative similarity is instantiated relative to two aspects. So we'll have that variation, and in general, you could probably also vary from this experience to this. I mean, I'm keeping it very general, so why not? But what I'm saying is I'll only draw in an arrow if that variation preserves a structural aspect that we have chosen. So maybe going from here to here preserves that aspect. And if it does, I'll draw in the same arrow on the left-hand side. So on the left-hand side, it now means that the variation has to preserve the mathematical structure S. Okay? So here I get it from data, and here I'm first of all drawing it in. It's going to be a condition in a moment on what counts as such mathematical structure. So maybe here's another arrow, and we'll draw it in. And now the idea is, that I've already indicated on the previous slide, is that we have the data. Data gives conditions on which variation, this is a mapping from the set of aspects here to the set of aspects here. And the data gives conditions for the mathematical structure on which of those mappings need to preserve the structure. So I'll indicate this here by equal, and this exclamation mark is mathematics notation for should be equal. Yeah? We're looking for an S such that these things are equal. The variations that preserve the structure are exactly the variations that preserve the aspect AS. And just again, so this is the intuition. So a mathematical structure is a mathematical structure of conscious experience if and only if something in phenomenology, namely the structural aspect AS, behaves exactly as the mathematical structure does under variation. What's hidden in here is an existential quantifier. So we're saying the message is we have a structure and we're looking for an aspect that behaves like a structure. The presentation I just presented, the way that I just presented this is the other way around. We have an aspect and we ask what are the conditions for a structure to represent that aspect. Okay, so far so good. Well, let's go back to our example of awareness then. Well, I've already indicated one model in the context of computational phenomenology of awareness. This is the model that the colored box on the right-hand side, if you remember, we'll come back to it in a second. And now I have another model. And I call this model W model of pre-reflexive self-awareness. And the W is inspired by this guy right here. This was one of the evenings at the conference. Really enjoyed this evening. We had guitars, we had singing. It was amazing in this beautiful Italian restaurant. And so thanks to all the musicians, and thanks in particular for Ken, who worked on this model, if I understood correctly, for a very long time already. So Ken is called Willie Ford, and therefore it's the W model of pre-receptive self-awareness. And as I said during my talk at the conference, it's always a bit dangerous if you summarize a whole paper, in particular a good paper, in just one formula. But for purposes of time, I'll do it anyway. So the W model consists of the following idea. C stands for consciousness. O stands for something else, perhaps contents of consciousness, perhaps other instantiated phenomenal properties. Let's leave it open for now. But the idea is that consciousness is both a relation, so that's indicated here. So in mathematics, a relation, a binary relation specifically, that's just an example here. A binary relation is just a collection of tuples. Tuples means two elements where the order matters. So this equal sign here just means that, and this is just a denotation for, these are just a notation for tuples. So this equal sign means that consciousness is a relation. But because consciousness also pops up in the relation, it is also what you could call a relation instance. It is an element of the set it defines. So roughly this formula means consciousness is both a relation and a relation instance. And that expresses some deep thoughts about pre-reflexive self-awareness, which for purposes of time I just can't go into right now. So I don't know if my explanation right now was intuitive. You should definitely look for that paper. I was unable to download this paper for reasons that have to do with publishers and commercial publishers and all that. So I just had to email Ken eventually, and it blew my mind. So I very much recommend you to read this paper. And what I want to say is that this idea that consciousness is both a relation and a relation instance is for me super intuitive. But I don't want to know what's super intuitive. I want to know why it should be true. Why is it the true? Why is the correct model of phenomenology? And so I'll say a little bit about this. And as I indicated before, like whether or not something is true really just depends, or not really just, but in particular depends on what we mean, by this being true. So it means on what we mean by attributing mathematical structure to conscious experience. So let me try to account for how we could ask this question in the context of the proposal that Tim and I developed. So I should say this is sort of, if there are any faults in this part, that's certainly my bad. I did talk about it with Tim, and he was also very much involved in coming up with the idea. But this is probably just, so it could well be my own misrepresentation that leads me to presenting it in this way right now. So this is the picture you just had, right? So the idea, just to correct, we have phenomenological data about variations, and they give conditions on what a mathematical structure has to satisfy. Well, what we can do now, we want to apply this in order to find out whether the W model is correct relative to this understanding of the foundations of mathematical phenomenology. We can just do the following. Well, I thought about this for very long. This was really a conundrum to me. How can we make sense of this in general? And so here's how I think we can make sense of it. So, and the funny thing is, it's very simple, as so often. So what we can do is we can literally consider an aspect of conscious experience that you could call membership aspect. So it's the experience of something being a member of something else. That's an aspect we can consider. That's a structural aspect or higher order aspect, right? The question is not what is a member of what, but the question is the experience of membership. Well, then we can apply the methodology. So we can say, well, so this is just abstract, of course. Maybe as we move from this experience to this one, this aspect is being preserved in the technical sense spelled out in the article. And maybe as we move from this tone to this one, it is also preserved. But maybe as we move from this one to this one, it isn't preserved, so we don't add this pink arrow here. And of course, then, as explained, this gives a condition on the mathematical structure that we can use to represent this membership aspect. And the condition and what this will give us is, first of all, we'll get a binary relation. So here I just used the symbol, the element symbol, instead of S here to denote that aspect. So we could also use the element symbol here to denote the binary relation that comes from this methodology. We'll get a binary relation, we'll know that from the start. And then the question which binary relation we get depends on sort of what these aspects are and which variations there actually are in experience. But abstractly speaking, it would look like this. We'll just copy the arrows from here to here. Now the task is we're going to have to search for a mathematical structures such that the arrows align as represented here, as presented here. Okay. And so this is not yet really helpful in terms of like the structure we just saw, W model. But here now hopefully comes the helpful part. This is just applying the methodology as usual with a specific aspect. But remember that the blue dots are sets of aspects. So what we can do is we can blow up one of these dots. So this is now, if you like, the aspects that are of one conscious experience, namely this one, right, presented right here. And what we can do now is we can now take the binary relation that we got from the methodology and we can represent that as a directed, potentially acyclic graph. That's always possible. And depending on what we got from the methodology, we could find a graph that only has these arrows. So this means this arrow indicates membership now. But potentially it also has these loops. Yeah, these, if you like, these arrows from an aspect to itself. And that would also indicate a membership. That would indicate something like the aspect is a member of itself. And that's great because this representation we basically get for free from the methodology is one way of representing non-well-founded sets. Yeah. So you can represent a set, or I should say this, sorry. A non-well-founded set is a set that allows things like having an element who is a member of itself. Yeah. Non-well-founded set theory is almost exactly as normal set theory, but changed a little bit so that you can have these things. And they're essential if you want to have things like relations that are also a relation instance. And it's sometimes also called hypersets. And the funny thing is that what we get from the methodology, we can present as that, and there's this link to non-well-founded set theory right away. Okay, so what this means is basically, it's not as great as I would hope to in general, but it's great for me personally, answers questions I had. So what this all means is that the methodology that we have can discover the type of structures used in the W model, right? It can be applied to see whether the W model applies, or vice versa. It can also be applied, presupposing the W model, to see what it means. So we can study the W model, and specifically we can study potentially its improvement, presupposing this methodology. But the big question, of course, is, so I said it can discover the type of DAO structures used in the W model, but the question is, does it? Yeah. And what I was originally hoping to do in that talk was that I wanted to present a few quotes from Thomas Metzinger's new book. Is it still new? I think it's already, the German version is already a year old, but still, to indicate that it does. But that's not really. So the question we're asking, first of all, is the W model a mathematical structure of phenomenology? So basically, is it the structure of what we call awareness of being aware, given the methodology I've introduced? And the point is that we don't know, and we cannot know in general. The answer is we need a phenomenological analysis, and such analysis is necessary to answer this question based on a suitable methodology. So what I wanted to say is I originally wanted to pull out a few quotes from Thomas and motivate it, but this would actually, I realized, be against the spirit of this talk. It would probably be nice, because maybe you'd share the intuition then that it's the right model. And I should say, I think the model and the intuitions or the reports from Thomas's book have not been brought together so far, so maybe it'll convince you. But first of all, when I finished the talk late at night at the conference venue, I think it was the evening where some people played the piano. Yeah, pretty sure. It was a wonderful evening. I think Thursday night. We had a piano in the conference venue, but still, I finished the talk and the book was at home, and I only had the PDF on my laptop, and I didn't have marks in the PDF, so I couldn't make the slide. But then I realized it's actually good that I can't, because that would speak against the spirit of the talk. Okay, so as I said, my personal intuition is currently clearly yes, but the point I'm trying to make is that intuition doesn't suffice for a scientific approach. Okay. So this was sort of the main message I'd like to drive home, and I'll come to one more thing, which I'll just say in a second. But I should add that it's very important to me to emphasize that we could have other methodologies. But I realized at the conference that it might be a bit misleading. I don't think we do have others right now. We have other methodologies for quality spaces, and they have deep problems, at least if we want to use them sort of outside their specific range of application right now. For example, if we want to use them to illustrate what is to be explained in a theory of consciousness. So we want to take these representations of phenomenology and then build theories of consciousness that target that representation. They're not good enough. And you can read up why in this paper I had on the other slide and in my structural turn paper. And I think for mathematical phenomenology, this is the first proposal. But I do want to encourage everyone to think about where it goes wrong, or maybe just talk to me, because I have a billion ideas of where it goes wrong and where it needs to be improved. Those are not concrete things, but abstract things. For example, I do think we need to represent in category theory, but I don't know how right now. I'm working on it whenever I find time. So there needs to be improvement, and we need to have better models that enable us to do mathematical phenomenology and that allow us to attribute mathematical structure to phenomenology more generally. Okay, so what I want to do in just the last few slides, I want to presuppose that the W model is correct. And then I want to ask, well, how could we implement the W model, if it is correct, into this sort of predictive processing-based active inference story of what's going on. And I'm asking this specifically because, as I said, there was the Minimal Phenomenal Experience project and the Minimal Phenomenal Experience track at the conference, which I very much enjoyed. And I think these are questions that are of interest to this project and generally people working on that. So how could we implement the W model in this type of active inference or predictive processing model? And sort of to disappoint right away, I won't be making an actual proposal, but I'll tell you how I think we could proceed. Problem is that the mathematics of the free energy principle is, from a mathematician's perspective, it is kept rather simple, right? This is basically very, very simple math. It looks complicated if you don't have a mathematical background or if you first see complicated diagrams like that. But what's going on is explained in simple math. So here's again a picture you might have seen from one of the papers where you see this this processing hierarchy. So you see the, if you like, the top-down hierarchy, but you also see the parallel hierarchy. And this is a picture I drew once for a completely different purpose to illustrate some of the key ideas. So you have somehow the signal arising in the brain, you have the prediction going up, the prediction errors going down. And I think the only chance we have to actually implement something like the W model into this predictive processing context is by generalizing the mathematics. So generalizing means we have to think about what the general most mathematical structure or mathematical theory is wrong. But I don't want to call it structure either. The most general mathematics are that allow us to represent the essence, or maybe even beyond the essence, all of what's in predictive processing free energy on the level of a framework, and sort of, but which are not married to the specific mathematics that are used in the literature right now to describe it. And I had a wonderful project on exactly that question together with my good friend and colleague Sean Toll and Toby Sanklier-Smithy. And we worked on basically providing a definition of active inference and predictive processing in category theory. So this is a paper we wrote together, a preprint right now, and you can all check it out. If you just Google it, you'll find it. And what we did there is we provided a definition of the theory in category theory, of active inference in category theory. And what's possible is that you can represent, even though category theory is super abstract, you can represent things in category theory in a very simple diagrammatic language, which ends up, it's different to the language that's usually employed, but it is very, very simple still. It is easily related, and is super general because it's actually talking about categories. So this language, I don't have time to introduce it right here, but so here are the usual interpretations of symbols, but just in a nutshell. So this language, for example, you can have hierarchies of models, so going upwards, basically top down. This is a generative model, but you can also have parallel processing. Yeah, that's indicated by these here. And these hierarchies really are just like, you can define very easily in terms of this string diagram language that you can use to describe the objects and morphisms of the category that are being involved. Okay, so that's what you can do. And now, if we now ask sort of how could we implement the W model in PP or active inference, and we have this general mathematical view of active inference in mind, right? We sort of have this very, very general account of what it means to do active inference in a category. What we can do is we can basically say, well, because a category theory is not married to set theory in any way, we can actually replace these spaces that pop up here. So in this language, the wires are the spaces, the boxes are the operators. We can replace these spaces or sets by spaces or sets from non-well-founded set theory. That's what we can do, right? And we can thereby incorporate or at least make room for structure as it appears in the W model. Okay, so first of all, this is, as I said, just a story about how I think it should be done. The question for me at the conference was, does anyone think it would be worthwhile in doing it? Because I think it's the right way forward if the W model holds true. But obviously, it's, first of all, it's a lot of work. And second, we get ourselves into this more abstract domain of things. And I don't know if people would actually find that helpful. And if so, I'd be interested, put it in the comments if you like, or send me an email, how they would find it helpful. It's always, there's always a danger in mathematical consciousness science that you do very abstract work that is so abstract that nobody really makes use of it. So if it's not very foundational, I think if it's foundational, it's always warranted. But if it's not so foundational, sometimes it might not be or it's not the nicest experience, or maybe it might not be super worth the effort if people then can't build on it really, because it's just in a more abstract setting than is customary in some field. Okay, so let me know what you think in the comments about this whole talk, by the way. Anyway, so the idea is that, just to summarize, if we want to implement the W model in active inference, we'll go to a more general account of the mathematics of active inference, and then we can basically start replacing the spaces, or in categorical setting, these are also called objects, of the model from spaces or objects from non-well-founded set theory or hypersets. So the last question I want to ask then, but of course, which spaces, right? I mean, you can't just replace them all, or we have to think about where the W model would happen. And I should say this is all related to something that's called coalgebra, and if you have an interest in that, please ping me. I don't know much about this yet, and I'm reading up slowly as I find time to see if I can push this further. Yeah, so which spaces? And here, the last slide of the talk is a slide which got lots of criticism at the conference, unsurprisingly maybe, which is really just my best guess of how I would approach the question of which spaces, right? Well, so here's a representation I really like that doesn't get criticism. I think that's okay. So we can actually not only think about the location, where does what happen in the brain, right? Where's the prediction error? But we can also think about the abstract process that takes place in the brain according to free energy and active inference between observation, sensory or interoceptive or something on the one hand, and then the determination of the hidden states in the model and the actions and policies that are being followed. That's a process that happens in your brain. It's not it's not one way only, and I'll just want to think about it abstractly. And now we can say, well, where in that process, which spaces, where in that process, which can be described by a generative model like this and its Bayesian inversion in the context of active inference, where in that process should we really try to situate the W model, if it happens to be the right model? And what I thought, my best guess right now, it's probably not such a good bad guess after all the criticism, is just to look at the theories we have. So we could look at the global neural workspace theory, where consciousness selects among multimodal parallel free energy subprocesses in this case, and it selects which result to distribute to all other processes. So maybe in this case, we'd rather look rather late in the process. We'd replace some spaces which are rather late, so which matter rather late in the model, whatever that may mean. Or maybe we want to look at higher order theories, according to which consciousness monitors, distinguishes, and selects among results of parallel free energy suppressors, and it selects those which it's supposed to make available to downstream processing. So I don't really know where to put the circle for that, but maybe you could think about, well, that's some intermediate domain, not as late as global workspace. We could look at the PP consciousness proposals themselves. So they are proposals also, not only, this is outside of computational phenomenology mostly. So they're proposals that just put the finger down and say, that's what I think consciousness is. So for example, there are proposals which say that consciousness is the generative model, that part of the generative model that contains a model of itself and how the model itself interacts with the world. Yeah? Again, so very broad circle. Or you could think about, well, maybe consciousness is self-evidencing. That's another idea, which means the internal states and their actions upon the environment are in the service of maximizing the evidence for their own existence. So maybe that has something to do with the priors, which are represented down here, the priors of our policies. And then finally, I mean, we could think about integrated information theory, which more or less says something like consciousness is the causal structure that does the cognitive processing, right? Okay, sorry, I don't know why I wrote that. That is way too general, but maybe that's something we could, yeah, that's why I wrote it. The idea behind integrated information theory, not the math. So maybe, I don't know, maybe the whole thing or something. So as I said, this slide took a lot of hits in the question time, so please ignore it. I just thought it's nice to start thinking about this. And obviously, like, maybe you have some good ideas, and then please put it in the comments. I'd be curious to see. Okay, good. That was my talk. Thanks for hanging in there. I didn't look at the time. I'm probably going to be very surprised how long it took. Rest assured that I presented all that in 20 minutes at the conference. And let me just give you the conclusions. So what I tried to say here is, first, computational phenomenology requires mathematical phenomenology. If you don't do mathematical phenomenology, if you want to do computational phenomenology, but you don't care about which math correctly describes phenomenology, you can do it, but it's there's not such a high probability of success, I would argue. Second, mathematical phenomenology requires a methodology. You can do mathematical phenomenology without an explicit methodology in mind, but it's not clear what you're getting out. Yeah, so it's something like it's super it might still be super worthwhile. It might still give a lot of nice interest, but there's no thing that determines whether what you say is right or wrong. Third, a methodology can be built on variations. That's what I explained, 2 different ways. And then I talked about the W model, and I wanted to say that my intuition speaks in favor of that W model of awareness. But of course, a principal analysis would be necessary. You really want to endorse this idea in a scientific context. And then finally, I talked about how to integrate the W model into the predictive processing or active inference context. Perhaps in a categorical setting by choosing spaces or objects from non-Wolf-founded set theory. Okay, that was my talk. Thank you very much to all those who listened who kind of listened to it at the conference, and also for you now for looking at the video. And yeah, I hope to meet you all at some future occasion. Bye-bye.